Hi gang, Comrade Ivan here. Our universe is 13,787,000,003 years old. How do we know that? Well, in 2018, astronomers calculated the age of the universe to be 13.787 billion years. 2018 was 3 years ago, so add 3 years to that. I gotta stop with these jokes. But how long could ETs have existed given this age of the universe? What is the oldest a technologically advanced alien civilization could be? Could they be millions of years ahead of us? Or could we be the first species to reach our level of technology, with others yet to follow? As it turns out, the time when carbon-based life could begin has a starting point in the universe, and we can't calculate it. The only problem is that we don't really know if life could come in forms other than carbon-based life that we see everywhere around us. And there's a good reason to think that way. During World War II, Allied forces were losing a lot of airplanes to enemy fire. They wanted to reinforce their aircraft to make them more resistant to shrapnel damage, but that meant making them too heavy for flight. So they decided to record where bullets and shrapnel holes most appeared on their aircraft and create a heat map of sorts. The idea was to then reinforce the areas marked in red in the hope that that would save lives and equipment. Abraham Wald was a mathematician who was assigned the task of applying the statistical analysis from the data on the aircraft that returned. And he came up with a suggestion that was not received without controversy. He made a point that this damage record came only from aircraft that made it back to the base. That meant that airplanes hit in the red areas could typically continue flying long enough to get to safety. He further recommended reinforcing the areas that had the least recorded damage. He correctly postulated that airplanes hit in those areas never made it home. This is known as the survivorship bias, and it could be argued that it's the reason why the idea of carbon life being the most prevalent form of life in the universe is so widely accepted. After all life here on Earth is carbon-based. So isn't it entirely possible that intelligent life could exist in a form that is so foreign to us we wouldn't even realize it's life, even if we saw it? Crazy as it sounds, we can't rule out that intelligent life existed perhaps as pure energy right after the Big Bang. Just like we can't definitively say that the ruler's name of the Galactic Council from Zeta Reticuli isn't Steve the Great. However, if we are looking at classical ETs, a little more complexity is required to form what we would define as life. Entities that utilize energy from some source to drive chemical reactions, what we commonly call metabolism. Entities that replicate themselves and are capable of evolving. This definition is good, but we can find examples all around us that don't quite fit those characteristics. For example, mules can't reproduce, but they're certainly alive. Viruses, on the other hand, do reproduce and do evolve, but they're generally not considered living organisms. They have no metabolism of their own. They're merely delivery mechanisms for genetic information that is copied by other organisms that themselves are alive. And then there are bacteria that have not evolved for 3.5 billion years, but we still do consider them alive. But they all have one thing in common: carbon. In spite of the survivorship bias, we can still safely say that carbon is the most likely candidate for a building block of life in the universe. And there are a lot of reasons why. Carbon is the fourth most abundant element in the universe, right after hydrogen, helium, and oxygen, none of which are versatile enough for life to be based on. Carbon is also lightweight, so on a newly forming planet whose crust is slowly solidifying, while heavier elements tend to ooze to the core, carbon readily accumulates on a planet's surface, making it accessible to life. At the same time, it can form a great variety of complex molecules due to its ability to bond with an extraordinary number of elements. At its simplest and its purest form, carbon is still one of the most versatile elements. It exists in as many as 8 states, some of which are plain weird. Take this carbon molecule, for example. This is Buckminster fullerene, named after Buckminster Fuller due to its molecular structure resemblance to the geodesic dome he designed. This carbon allotrope, also known as buckyball, behaves in mind-boggling ways. Check this out. If I shot a bunch of marbles through 2 slits in a barrier, only the marbles that don't hit the barrier would go through. No surprise, they would form a pattern of 2 lines where marbles went through the slits. If I fired a wave, say I shot some light at the 2 slits, the 2 waves that form on the other side would interfere with each other. In areas where a crest of a wave meets a trough, they'd cancel each other out. So you'd see this type of a pattern on the barrier behind. No surprise there either. What is surprising is that if you shot an individual photon, just the most fundamental unit of light, and then kept on shooting one after another, the pattern they would collectively leave on the barrier behind would look nothing like what marbles leave. The pattern would be identical to that of a wave. It's as if each photon goes through both slits at the same time and then interferes with itself on the other side. And if you were to put a detector to see which slit the photon went through, you'd not only find that the photon went through only one slit, but a pattern would disappear. This behavior is well established in the field of quantum physics. Tiny particles like photons and electrons are quantum particles. They're the most basic units of energy. And quantum particles have wave-like properties. They're quite literally in a whole field of locations at the same time. But once observed, they snap out of this state and behave as individual particles. Buckminster fullerene, though, is not a field or a wave, if you will, nor is it a particle like an electron or a quark. It's an object made of particles. It's a very small object, but it's as much a classical physics object as a marble would be. Yet it too has this weird wave-particle duality. A single buckyball fired at the slits acts as if it goes through both of them at once, unless it's being watched. That is weird. Carbon is amazing. Carbon-based life makes so much sense that most scientists agree that if life existed anywhere else in the universe, it would probably be carbon-based. In fact, this view is so prevalent that any opponents call it carbon chauvinism. They point out that there are other elements on the periodic table, such as silicon, which are also capable of forming complex molecules. Silicon is also light enough to accumulate on the surface of a molten planet and abundant enough to allow life to take foothold. This view is valid, but it doesn't really help us in determining the era an early alien civilization could have first formed. All elements heavier than hydrogen are created inside stars and then dispersed through space, either when a star sheds its outer layers before collapsing into a red dwarf, or more commonly when it explodes in a supernova. You and I are both made of stuff that was once inside a star. Consider that next time somebody tells you you are hot. The processes by which these elements are created are very well understood, and we know that carbon is made first and in greater quantities than silicon. So then the question really is, how long does it take to make carbon in sufficient quantities? If you ever used a hand pump to inflate your bicycle tire, you may have noticed that the pump gets hot quite quickly. This is in part due to friction, but most of the heat is due to compression of gases that make up air. When gas is compressed, it heats up. You can think of it as taking a small amount of heat spread in a large space and concentrating it into a large amount of heat in a small space. Stars get created when hydrogen cloud collapses under its own gravity. It becomes so hot and its atoms smash into each other with such gusto, they start a fusion reaction. But collapsing hydrogen builds up heat way too fast. It gets too hot before enough of it is in one place for gravity to take over and drive this collapse further. We can see it in this bottle here. As I submerge it in hot water, the gas inside it heats up and it starts to exert pressure on the soap bubble on top. Luckily for us, these days, large hydrogen clouds have other elements mixed in with them, elements left over from the time older stars have exploded when they went supernova. These elements act like sponge for heat. They absorb it and convert it into photons. Light. Light travels at the speed of light. So this heat leaves the cloud quickly. This cools the cloud fast, so many pockets of lower temperature appear within it. Because there are pockets of lower temperature, the hydrogen has less pressure inside it and gravity can take over again. This is how stars are born today. But that wasn't always the case. The early universe didn't have any elements heavier than hydrogen or helium. So there was no way for a large cloud to cool small pockets of gas and allow a bunch of stars to form. Instead, the heat just kept on building and building and the cloud got bigger and bigger. It took a long time, but eventually the cloud as a whole became so hot that it started a fusion reaction on a massive scale. Since there were no cold pockets where smaller sun-like stars could ignite before all this gas accumulated in one area, there wasn't anything to blow this extra hydrogen away and stop this growth. As a result, stars that were born in the early universe were huge, more than 50 times the mass of our sun. Their upper end size is heavily speculated, but some of those stars may have even been as large as 1,000 times the size of our sun. And they didn't take their time to make carbon. No. Earliest stars were too large to burn at the meager 15 million Kelvin like our sun does. No, they burn at several 100 million degrees. Anything burning that bright burns fast. Take our sun for example. By the time it dies, it will have reached the ripe age of 9.5 billion years. Compare that to early stars. They would burn up and explode in just 1 million years or just slightly more than that. If you think that 1 million years is a long time, think again. Compared to 9.5 billion years, that's what a baby born 2 days before yesterday is to a 78-year-old. And when these babies blew up, they were supernova to behold. They were capable of blowing up small galaxies. They seeded the early universe with carbon, but the quantities needed for complex molecules didn't build up until much later. The year was 4,788,000,000 after the Big Bang. It was a beautiful Wednesday, 18th of July. Sky was actually bluer than blue. It was ultraviolet. But it was a day when life finally got its first chance to come into being. The first life in the universe. It was not a Wednesday, by the way, I totally made that up. But extrapolating from what we know about life here on Earth, it's fairly likely this did happen 8,999,000,000 years ago, give or take 20 million years. Because life here started as soon as it could, and it populated the Earth fast. Since the time microbes first showed up, they continuously dominated the Earth. There's more bacteria on Earth by weight than all animals and insects put together. It's estimated that there are over 1 million bacteria on our planet. That's a 1 followed by 30 zeros. If you were to line up all these bacteria side by side so that they're touching, they would form a string well over 105 million light years long. Our galaxy is only 105,000 light years wide, so you would be able to fit 1,000 Milky Way galaxies in the same width. That's a lot of germs. But how long does it take for intelligence to emerge from all this bacteria? All life on Earth currently shares a common ancestor. Might I share a parent with this guy? Likely not. But what about a grandparent? No. But if we were to go back enough in time, we would find a common many times great grandparent to both you and I and Joey here. We can actually see this in the DNA of every living thing on Earth. It's a living record of your family tree. I may do a separate video on it someday, but if you're interested in how scientists tested and proved evolution experimentally, I highly recommend the book The Greatest Show on Earth by Richard Dawkins. In any case, the length of time between the common ancestor for all life on Earth on one side and first humans on the other is discouragingly long. I say discouraging due to the window of habitability. The window of habitability refers to a period during which a planet exists in a Goldilocks zone. This is an area within a star system that has a temperature that's neither too high nor too low for life to emerge. In our case, the window of habitability is nearing its end. In about 1 billion years or so, the sun will become 10% brighter than it is today. That might not seem like a lot of extra brightness, but today the sun is already 30% brighter than it was when it first formed. Adding another 10% of today's brightness might be a small inconvenience for our eyeball holes, but impossibly bad news for life, because the Goldilocks zone will fall outside of Earth's current orbit. The window of habitability started at the end of the period called the Late Heavy Bombardment. Now, this is a period during which Earth was just pummeled with dinosaur-ending-sized rocks, one after another. It was a time that was absolutely inhospitable to life. And here's how you could imagine what this could have looked like. First, think of the meteor that ended the dinosaurs. It released 7 billion times the energy of the Hiroshima bomb. 7 billion. You and I and Tom Scott and everybody else make up for just about that many people. Imagine giving every living person on planet Earth a Hiroshima-sized nuclear weapon and then having them all trigger it at the same time. That would be a bad day. But that's small potatoes compared to what we got hit during the Late Heavy Bombardment. The stuff that hit us back then was roughly between 3 times larger and up to 30 times larger. And that kept on hitting us over and over again. Now that is a Late Heavy Bombardment. First life appeared as soon as this period ended. And if you were to reduce the entire history of all life on Earth, roughly 4 billion years, to just a single human lifespan, 80 years, the first Homo sapiens arrived just day before yesterday. And by the time our sun becomes hot enough to evaporate all oceans and sterilize the planet, on the same time scale, that human will be turning just 18 years of age. If intelligence arrived on Earth just 1/5 of the time later than it did, it would have had no chance of survival. The Earth would have been too hot for us to even show up. We literally snuck in at the last minute. And speak of the dinosaurs, we're only here because of a cosmic roll of dice. If the meteor that killed them off didn't strike when it did, it's likely that life on Earth would have emerged, matured, and died off without any of us to think about its existence. Intelligence is rare, and here on Earth it took a long time for it to evolve. If intelligence needs an Earth-like planet revolving around a sun-like star, and it takes as long as it took here to appear within the window of habitability, animal life on another planet had a slim chance of ever becoming smart. Besides, intelligence is not necessarily the inevitable outcome of evolution. Richard Dawkins points out that evolution is all about resource management. In order to survive, organisms tend to evolve to use fewer resources, so it's entirely possible that evolution gives greater advantage to growing large fangs than the large calorie-hungry brains at the expense of all other defense mechanisms. But if intelligence is inevitable, and if it does take as long as it took here on Earth, the earliest civilization at our current level of technology could have invented YouTube of their own as early as year 8,558,000,000 after the Big Bang, on a beautiful sunny Wednesday, 18th of July. Unless the entire universe had a habitability window of its own. Avi Loeb, a professor of science at Harvard University, came up with an idea so brilliantly simple, it's amazing no one ever thought of it before him. He realized there was a time when the entire universe was a Goldilocks zone. After the Big Bang, the universe was way too hot for life. But as it cooled down, there was a time when even a planet ejected from its own solar system, or even its galaxy, would have been basking in the leftover heat coming from every direction. Today, this heat can be observed as cosmic background radiation. But while today its temperature is just 2.73 degrees Kelvin, 270 degrees below freezing, there was a time when even a rogue planet would be able to support liquid oceans, and therefore life. In Loeb's 2014 paper titled The Habitable Epoch of the Early Universe, he calculated this period to be just 10 to 17 million years after the Big Bang. The conditions which would allow formation of Earth-like planets this early on in the universe were not ideal. But it is possible that there were pockets in the universe, however rare, where just the right conditions existed. If life emerged in such conditions, it wouldn't have had much time to develop intelligence. And in an extremely unlikely scenario that this did happen, in a cooling universe, there would be very little they could do to avoid their extinction. The best they could hope is to imagine that one day another civilization would look back at their time and wonder about their existence. We will never be able to communicate with them, but we can feel a sense of communion, much like we do when we look at the stars and think of the civilizations that are likely looking back at us across the gap of space right now. This may be why in 1974, Frank Drake, along with Carl Sagan and a few other astronomers, decided to try to bridge this gap. They created a short message that was beamed from the Arecibo dish in Puerto Rico to anyone listening in the Great Globular Cluster in the constellation Hercules. The message was comprised of 1,679 pixels, a number that's a product of two prime numbers, 73 rows and 23 columns. And it was attempting to relate things about us, like the base 10 numbering system that we use, the makeup of our DNA, the average height of a human being, a graphic of a solar system, and a few other basic pieces of information about us. We did our best to come up with a message that was easy to decode, but when given to a bunch of experts from the field in the time since the transmission, no one was able to decode its meaning. A message constructed by us and attempting to explain what and where we are couldn't even be read by humans. So the next time you're out, look up at the night sky and ask yourself if there's someone out there looking back at you. An endless universe is probably teeming with life. So it's likely that someone somewhere out there is doing the same this very second. You're still here? Awesome. Let me ask you a question. Have you ever had a déjà vu? Some people actually believe that the feeling that we've experienced this moment before was explained in the movie Matrix, that we're all living in a computer simulation and that déjà vu is just a computer glitch. I know it's crazy, but how do we know for sure that they're wrong? If we all lived in the Matrix, all evidence of life outside it could be obscured from us, and all evidence that we are delusional could be manufactured. Or could it? In the next video, we'll delve deep into all available evidence for and against the idea that everything we see is a simulation. If you're already subscribed, you're awesome. Just make sure that bell icon is set to all, otherwise YouTube will not necessarily notify you when the next video is out. And make a comment about topics you'd like to see covered in future episodes. I promise you I read every single last one of my comments. If you're not subscribed, I'm not going to ask you to do so. We're all grown people out here and we can decide for ourselves what we want to do, right? Or can we? Check out my previous video about the evidence for and against the ability to make free choices. You might find the information in there surprising. I know I did while I did the research. The link, it's in the description. Cheers.